Hello guys, we will continue with our NLP playlist, and in this video we will understand what is GRU, how it works and how it is different from a standard LSTM block. So GRU is short for gated recurrent unit and it is a modification of a standard LSTM block. I have explained LSTM in 3 parts in detail, so I request you to go and watch those videos. But if you haven't watched that, you don't know anything about LSTM, it's okay. I will explain GRU in detail, right, from end to end. So for those who already know LSTM, you know that it has 4 hidden layers, right? So let me just write some small comparison between LSTM and GRU. So LSTM has 4 hidden layers, okay, and how many gates it has? It has 3 gates. Okay, GRU has 3 hidden layers and 2 gates. So as you can see from this particular block here, it has 3 hidden layers, whereas LSTM had another hidden layer here. Since we have one less hidden layer and one less gate, number of params in GRU, number of parameters in GRU is less than that of LSTM. So since the number of parameters, or we can say trainable parameters, are less in GRU, it is comparatively faster to train. It is comparatively faster to train than LSTM, and also the performance is also comparable. It's not that we have simplified the LSTM so the performance will get degraded. No, in some of the tasks GRU is said to outperform the performance of LSTM, but it's not the case for all the tasks. Okay, so in few of the tasks we still need to use LSTM. Okay, so now what is the main idea behind GRU? So the main idea is 2 separate states are not required to carry both long-term context and short-term context, right? So in LSTM you see there are 2 outputs, right? So AT, and there is something it's actually called as CT in LSTM, and we have AT. So those 2 are separate. So one is to carry long-term context, another one is to update the short-term context in the long-term context. But in gated recurrent unit, in only one cell state, we will be able to carry both short and long-term context. How we will be able to do that? It will be with the help of 2 gates. One is reset gate. It is also called as relevance gate. So let me just write it down. Relevance gate. I personally would like to call it as relevance gate. Why? I'll tell you in a while. But most of the guys and also in literature, I think they have referred to it as reset gate. So for my next explanation onwards, I will use reset only. Okay. And the second gate is update gate. Okay. So if we understand how these 2 gates, reset and update gate, help in carrying STC and LTC in single cell state, it will be done deal for GRU. Okay. So let's start. As you can see in this particular diagram, it represents a single GRU block. Okay. And it has one output at time step t. Okay. So let's take it slowly. Please watch this video till the end so that you will have the complete understanding. Okay. Now, before we jump in much detailed explanation on these components, let us first understand the components that are present here. Okay. So let me first write the components. Okay. So the first thing, as you can see, it is activation or the cell state from previous time step t minus 1. Activation of the cell state at the current time step t. Third, input at the current time step t, that is xt. Fourth, we have reset gate. Fifth, we have update gate. And sixth, we have something represented as a bar t. So this is our candidate for update. Candidate state for updating AT. Okay, you can say updating or calculating AT. This GU is update gate. This GR is reset gate. You know, this is input, this is activation at time step t, or you can say cell state at time step t, and this is from time step t minus 1. Okay, and remember, all of these are vectors. All of these are vectors. And except xt, dimension of gr will be equal to dimension of gu. It will be equal to the dimension of at, will be equal to the dimension of at minus 1. Okay, and also a bar t. All these dimensions will be same. All these will be of same dimension. And also remember, these are all the vectors. And how many dimensional vectors are they? It depends on us. We have to decide that. Depends on us. Okay. And when we decide that, I'll tell you in a while. And what about this xt? This is actually our input, right? So this dimension of this actually depends on the number of features that we have. Number of features that we have. Okay. So let's say if we say that at minus 1 is a vector of 4 dimension. Let's say at minus 1 is a 4-dimensional vector. So gr, gu, at, a bar t all will be 4-dimension. Okay, just remember that. Now we have seen the main components, the outputs and inputs that we want. We will understand what these boxes here. Okay, so these boxes here, which are in yellow color in this diagram, so these are all our hidden layers. These are our hidden layers. Okay, and these are all neural network layers. Neural network layers. And one more thing, they are all fully connected. Fully connected. So when I say they are all neural network layers, how many neurons they have? How many neurons they have? So it actually depends on us. We have to decide that. Depends on us. We have to decide that. So this is actually a hyperparameter. Okay. And now coming to an interesting point. So the number of neurons in each of these layers should be same. Okay. So it should not be the case that in first hidden layer we have 4 neurons, in second hidden layer we have 3 neurons, in third hidden layer we have 5 neurons. No, this won't work. GRU will not work like this. Okay. So the number of neurons in all these 3 layers should be same. Okay. Should be same in all 3 layers. And one more important thing and interesting thing, the number of neurons in these hidden layers will decide the dimensions of GR, GU, AT, AT minus 1 and A bar T. Okay, you have to understand this. How the number of neurons in the hidden layers will determine the dimension of these outputs, gates and the candidates. Okay, and it will be equal. So if we have 4 neurons in the hidden layer, all of this will be vectors of 4 dimension. Okay, so hope that is clear. Now you can see some symbols here, right? Multiplication encircled, addition encircled and 1 minus. So let's understand what are those. So this multiplication encircled, it's called as point-wise or element-wise multiplication. The technical term for this is actually Hadamard product. Hadamard product. So you don't have to remember this particular name, but it's just good to know. Okay. Now this symbol plus encircled is point-wise or element-wise addition. Okay. And this 1 minus, I will tell you when we talk about computing AT. I will talk more about this 1 minus symbol you can see here in this diagram, right? So I will talk about this later. Now we have understood the components and the symbols associated with GRU. Let us first jot down the steps in GRU. How GRU works. So this GRU works actually in 4 steps. So we have totally 4 steps. step 1. So what is step 1? To calculate reset gate. Reset gate represented as GR. What are the inputs for this? Inputs are, if you just look at the diagram here, let me copy this so that I won't have to scroll it again and again. Okay, so the link is missing. Let me quickly draw that. So there is a link from here to here. Okay, so if you see for GR, what are the inputs? It is XT, right, and AT minus 1, correct? So AT minus 1 comes from this connection and XT comes from this connection. So let me just write it down, XT comma AT minus 1. So this will have the weights associated with it, and let's represent it as WR, and bias, let's name it as BR. So WR weights, this will be a matrix of some dimension, and this will be a vector. Okay, this is a bias. So this is first step in GRU. So how do we calculate GR? Let's write that equation now with the help of inputs and the weights that we have written down. GR is calculated as, it is sigmoid of WR, and it is concatenation of XT and AT minus 1. XT comma AT minus 1, and the bias associated will be BR. Okay, so this is how we calculate reset gate or relevance gate. Okay, now if you want to work out the dimensionality, you can do that. So let us first understand what we mean by this representation. So this is called as concatenation of two vectors. Okay, so we have fixed, so let us fix the number of features and the number of neurons in the hidden layer. Okay, so number of features, let us fix it to 5, and number of neurons in the hidden layer, let us fix it to 4. So why I am assuming few things? In order to help you guys understand the dimensionality of these gates. Okay, so since we are concatenating XT and AT minus 1, let me just draw that. So XT, okay, so we have 5 input features, and AT minus 1 will be of 4 dimension, right, because number of neurons in the hidden layer is 4. So this part here is XT, and this part here AT minus 1, and we are concatenating it together. We will get a vector of dimension 9. 5 plus 4, 9. Okay, so now we will have our hidden layer, the size of which is 4. We have 4 neurons, and this is a fully connected neural network. You have to understand that it is fully connected neural network. When I say fully connected neural network, every neuron in one layer will be connected to every other neuron in the next layer. So that's what we call it as fully connected. And how it looks something like this. So if I just draw the connections here, I'll just draw it for 1. You can make out for the rest of the neurons from input to this hidden layer. So like this, the connections will come from all the neurons to all these neurons in the hidden layer. Okay, you can draw for the rest of the things. Now, since this is a neural network, it will have the weights associated, right? Now we are calculating GR. Let's call that weight as WR, and the size of this will be 4 by 9. Okay, so now let's work out the dimensions. Dimension of this is 4 cross 9, and this is 9 cross 1, right, and plus bias. This will have the bias, let's call it as BR, right? So it will be of dimension 4 cross 1. Now this here, this thing here is matrix multiplication. Okay, so since we are doing matrix multiplication, the resulting output of these two things will be 4 cross 1, plus we are doing the addition of another vector to this 4 cross 1 vector. So the resulting output, that is GR, will be of dimension 4 cross 1. Okay, fine. Now we are done with reset gate or relevance gate. Now let's go to step 2. Okay, so step 2 is to calculate the candidate for updating activation or cell state at time step t. So the candidate is represented as A bar t. Okay, so what are the inputs for this A bar t? If we just look at the diagram, the inputs are xt. Okay, we are getting the current input at the time step t, and then we are getting this particular input here, at minus 1 pointwise multiplied by gr. So these two are our inputs. So let me just write it down. What are the inputs? xt, it's common for everything. Input xt is common for everything. Okay, let's not worry about that. The important thing is this particular thing, the second input for A bar t, that is at minus 1 pointwise multiplied with gr. So that is a t minus 1 pointwise multiplied with reset gate. So these are the inputs. Okay, and what is the activation? Tan h. Activation tan h. And by the way, in step 1 the activation is sigmoid, correct? So I haven't written that. Let me just write it. Activation sigmoid. Okay, now coming back to step 2. Now what we have to do, we have to compute A bar t. So this will have its own set of weights associated with it. Let's call it as WA. Okay, so how do we calculate A bar t? So it is simple. If you just look at the figure, A bar t, it will be equal to tan h is activation, right? So tan h of weights associated with it, that is WA. Inputs are xt and this particular thing here, A t minus 1 pointwise multiplied with reset gate, plus the biases, let's call it as BA. So how this looks like? So as we have drawn the neural network for the first step, that is calculating reset gate, we'll try to do the same thing here. Okay, so xt is again having 5 features, so we have fixed that, right? We will not change that. at minus 1 and gr, these two, these are 4-dimensional each, right? And we are doing pointwise multiplication. So if I take 1 2 3 4 and consider this as at minus 1, and if my gr, so since it is sigmoid, all the values between will be between 0 and 1, right? 0.5, let's just consider 0.5, 0.5, 0.5. What we are doing? We are doing pointwise multiplication between these two vectors. So each of the values will be halved. The output will be 0.5, 1, 1.5 and 2. So this is the output of this. Again, the dimension will be 4. So I'll just write 4 inputs for these things. And these two are concatenated, right? So together we have 9-dimensional vector. So this part here till this, it is xt, and this part here it is at minus 1 pointwise multiplied with gr. Okay, now this will be connected with hidden layer. And how many neurons we have in the hidden layer? We have set it to 4, correct? And again, this will be a fully connected neural network, as I explained to you guys in the reset gate step. So it will be a fully connected layer. So the gates associated with it we will call WA, as we are calculating A bar t, and it will be of dimension again 4 cross 9. It will have the biases, we will call it as BA. It will be of dimension 4 cross 1. So now if you work out the dimensions of this particular equation here, so this is 4 cross 9 matrix. We are doing matrix multiplication with, what is this? This is 9 by 1, right? So 9 by 1 dimensional matrix plus BA is of dimension 4 cross 1, right? So this is a matrix multiplication. So if you can figure out the dimensions, the output of this will be 4 cross 1, adding with 4 cross 1 vector. So the final output will be again 4 cross 1. So this is the dimension of our candidate A bar T. Okay. Hope it is clear. Now we have the candidate A bar T. We will compute our update gate. Okay. So how do we calculate update gate? So that is represented as GU, update gate. So is this the second stage in this? Yes. In step 2, A, B. Or let's just call it a step 3. Okay. So step 3 is calculating GU. So now if you look at this block again, GU is here. And what are the inputs to it? It takes AT minus 1 and XT. Same inputs. So inputs are AT minus 1 and XT. Weights associated will be WU, bias will be BU. Now let's write out the formula. As you might have already written it, guessed it. It will be sigmoid, right? So it's a sigmoid function, sigmoid activation function here. So sigmoid of WU concatenation of XT comma AT minus 1 plus BU. Okay. Dimensions, you can work this out as an assignment and then you will get to know that GU will also be of dimension 4 cross 1. It has to be. Otherwise, we are doing something wrong. Okay. So, and it will be 4 cross 1. Don't worry. Now that we have everything, update gate, the candidate, and also the reset gate, we will finally compute AT in our fourth step. So, what is this AT? The cell state, right, at time step T, at time T. So, how do we calculate it? Let's take a look at the figure once again, right, here. So, if you check here, we are doing A bar T. We are taking A bar T as input. Let me just write it, okay. A bar T is one input, GU is another input, okay. So, let me just write. So, it is inputs are, let me first write the inputs. It is A bar T, GU, right. First, these two are the inputs, A bar T, GU, and then we are getting AT minus 1, doing pointwise multiplication with 1 minus GU, right. So, let me just write A T minus 1, that funny symbol 1 minus, and also GU. So, these are our inputs to calculate AT. Now, let's write out the equation. So, AT is equal to, first write this out, AT minus 1, pointwise multiplication with 1 minus GU. Okay. So, that is A T minus 1, pointwise multiplication with 1 minus GU. So, this is the first part. So, we have written the equation for AT by considering this thing here. Okay. Now, we have to consider this part here. Let me just change the color. So, we have to consider this part now. So, that is GU into A bar T. When I say into, it's pointwise multiplication, right? So, let me just write that. GU into A bar T, right? GU into A bar T, and in the end we are doing pointwise addition between this component and this component. So, we will just say pointwise addition. Okay. So, this is how we calculate the current cell state or cell state at time step T. So, congratulations, we have arrived towards the end of computations, but still we have to understand how this works. Okay. So, let us see that now. Now, if GU, so what is GU? It is update gate, right? Update gate, correct? So, and it is having activation sigmoid, right? So we know that output of this or the values of this will be between 0 and 1, right? So what happens if all the values are 0 for GU? So what happens if it is a vector of all zeros? So what we do? We are multiplying AT minus 1 with 1, because 1 minus 0 is 1, and this, since GU is 0, the candidate values will be turned off, right? So the current state AT will be equal to AT minus 1. So in this way, what we are doing in this case, we are propagating the context from time step t minus 1 to t. Okay. So what if all the values in GU is 1, 1, 1, 1, 1. It's a vector of all ones. So what happens in this case? So in this case, what we do? AT minus 1 into 1 minus 1, that is 0. So AT minus 1 will be turned to 0. Since GU is all 1, we are doing AT is equal to A bar T. So in this case, what we are doing? We are forgetting everything. We are forgetting everything from what? We are forgetting everything from AT minus 1. Correct? Hope you are getting it. Okay. So similarly, if the values of GU is 0.5, 0.5, 0.5. So in this case, we are forgetting 50% of the information from previous time step and adding 50% of the information which looks to be relevant at the current time step, and we are getting it from A bar T. So one thing to remember here is A bar T is not our final required output, it is AT, right? So how AT is calculated? With the combination of A bar T and AT minus 1, and with the help of these gates. Okay, hope it is clear. If you have any questions, please reach out to me. Okay, so did we talk about A bar T earlier? Yes, we have talked about A bar T here, right? So now in this calculation AT, we have only seen or made use of update gate, right? So where did this GR or reset gate go? Where did this reset gate go? It is already combined or included while calculating candidate T. Okay, so this is the equation. So let me just write that down again below. So how do we calculate A bar T? So it is of I think it's of tan H, right? So if we just look at here, yes, it's of tan H, correct? So let me just write that out. So it is tan H WA XT, I think it's AT minus 1 multiplied pointwise multiplication of GR plus BA. Now we have to talk about this particular thing here. What we are doing? AT minus 1 multiplying with reset gate. I told you I like to call this as relevance gate. Now I will tell you why. Okay. So what is this GR? GR is also a sigmoid activated values, right? So GR will also be values between 0 and 1, right? So what we are doing? We are doing pointwise multiplication of values between 0 and 1 with previous cell state at previous time step. Again, what happens? So if we have some information 5, 10, 6, 8, something like this as AT minus 1, and if GR, let us, for simplicity, let us just assume we got all 0.5s here. So it's not necessary that all 4 values should be equal, it can be different. Okay. So now what we are doing? We are doing pointwise multiplication with 0.5 vector of all 0.5 values. So what happens? The output will be 2.5, 5, 3, 4, right? So output of this will be these values. So if you compare it with AT minus 1, so we are losing about 50% of the information, which we think, or at least GRU thinks, is not important. We are losing 50% of the information. At this particular step, 50% of the information is lost. If GR is a vector of all ones, we are not losing anything. We are carrying this as it is. So the output of this will be again 5, 10, 6, 8. So we are not losing anything. So this relevance, this GR in a way tells us how much relevant is AT minus 1 to compute the candidate at time step t. Okay, I'll tell you again. This GR, what we call it as a reset gate, GR, we call it as a reset gate. It actually tells us how relevant is cell state from previous time step in computing AT, the candidate at time step t. Okay, so since this controls what and how much information should be passed to candidate at time step t, I would like to call it as relevant gate, right? So if you read it in this way, how relevant is AT minus 1 in computing the candidate A bar t, you would have an idea as why I like to call it as relevance gate. Okay, so hope you guys are clear on GRU and how GRU is able to carry both long and short term context with the help of only 2 gates. So I have already explained it here. So let me just explain it again. So I'll just write the expression for AT again here. So AT is equal to, so it is 1 minus AT minus 1 into 1 minus GU, right? So AT minus 1 into, this is pointwise multiplication, 1 minus GU, pointwise addition, GU multiplied, pointwise multiplication with A bar T. So this is our final output. And now we will once again understand how this is able to carry the long term and short term context both. So if GU is vector of all 1, this will set AT is equal to A candidate T. Okay, because if it's 1, 1 minus 1 is 0, T minus 1 would be lost and the current context will be used. Okay, and not all the current context will be used. Again, A bar T is calculated using the relevant gate, right? So it depends what kind of information we are actually passing through. But for sure, the previous time step context is lost. Not completely, because we also have this A bar T, which is computing the values based on the previous time step with something called as relevance gate, right? So this is the case if GU is all 1. So if GU is all 0, then AT will be equal to AT minus 1. So there is no other point in discussing here, right? So we are just passing the context from the previous time step as it is to the current time step. That's it. Okay. So hope this video is clear to you guys. This is how GRU works. I know this video is long, but for the sake of simplicity, I have taken much time and divided this block into multiple steps so that you will be able to understand it easily. So if you guys have any questions, please reach out to me via comment sections. If you guys have not subscribed to my channel, please do subscribe. And also, if you're liking the content, give it a thumbs up and share among your peers so that they will also get benefited. Okay. So till we see in the next video, happy learning. Bye bye.